Hey kids, do this practice problem. Good job, you got it. The answer is choice 2, 3.7 times 10 to the 6 newtons. Quick note, the Earth's radius is like 6.4 times 10 to the 6 meters. So if this space station was on Earth, its weight would be 9.8 times mass, or about 10 times mass. If this was on Earth, the answer would be 4.5 times 10 to the 6 newtons. The answer is 3.7 times 10 to the 6 newtons. So it's less, but it's not much less. It's only a little bit less. And this we'll come back to in the future. Space stations and space shuttles in orbit around the Earth, they're not that far from the Earth. And their weight is not that much less than their weight on Earth. They're still pulled to Earth by almost the same amount of gravity. We'll come back to that later. Today we're talking about circular motion. We're going to keep it real simple when we start out, obviously. You guys probably haven't seen these in a while. Remember these like, lanyards? Wow, pretty fancy stuff. So let's say I'm spinning my keys in my hand in a circle. And just assume, you can't really tell. I guess I'm only 30 FPS, so it's not that weird. So we're going to make a couple assumptions, real simple assumptions. Assume constant radius, constant speed, it's a perfect circle, constant radius, constant speed, perfect circle. It's a flat circle, like a two-dimensional circle, no like up and down motion. And we can't assume constant velocity. Why can't we assume constant velocity? Yes, Daisy? An object going in a circle can't have constant velocity because its direction is changing. Yes, good job. Thank you, Daisy. Yes. So we'll assume all these objects are moving with constant speed. They're not speeding up, they're not slowing down. That does not mean they have constant velocity. They can have constant velocity. When you go in a circle, you change direction all the time. In fact, you're always changing direction. If I drive my car in a circular path in a if I run in a circle in a tree, I'm constantly turning the whole time. My velocity is always changing, but my speed is not. At least that's what we're assuming until a very, very juicy unit in later this year. So today we're talking about circular motion. We already learned two important terms about circular motion. Period and frequency. We learned them in our lab on pendula, but they have the same meaning. If something's moving in a circle, the period is the period of time per cycle. It's how long it takes my keys to swing in a full circle. Frequency is how frequently they go in a circle. It's the number of cycles or circles in 1 second. For my keys, it's probably like 1 or maybe even less than 1 cycle per second. But something spinning really fast, like a CD, you guys probably don't even know what those are anymore. Might have a frequency higher than 1. They might have like 20 rotations per second, something like that. So that's pretty straightforward. So we got a nice object going in a nice circle with velocity v. Here's the center of the circle. How do we find the velocity of this circle? How do we find the speed or the magnitude of velocity? Ooh, I know. Yes, Hazel? Velocity is displacement over time. Yeah. and speed is distance over time. So then what? Well, the displacement is circumference, and the time is the period. That's right, yeah. In one period of revolution, the distance traveled is 2 pi r, the circumference. And in this case, speed is the same as magnitude of velocity because it doesn't change. This never changes speed, never slows up or slows down, or never speeds up or slows down. The velocity changes direction, so the velocity changes, but the magnitude of velocity doesn't change. And the magnitude of velocity is the same as speed. And that is 2 pi r over t. You could also say it's 2 pi rf, because period is 1 over frequency, and frequency is 1 over period. Wow, physics. Great job. Okay, now for something completely unrelated. WALL-E spoilers. You guys ever see WALL-E, where this little robot gets lost in space? And this is a very common space movie trope. He uses a fire extinguisher to
9, 8, 7, 6, 5, 4, 3, 2.
Well, in theory, that would work. In theory, an astronaut or a small robot could use a fire extinguisher to move through space, as long as the fire extinguisher didn't freeze and break or something weird like that. So that might work in theory. What if you try to use a fire extinguisher to push a whole spaceship? Let's say I have a full spaceship 200. Alright, the spaceship's thrusters and engines and whatever stop working. But it's okay, because you stick your body out the window and you use the fire extinguisher. Oh, of course you have a space helmet too. So let's say this is a whole giant rocket ship. It's super heavy, has lots of mass, and it's already moving with speed v. So 3-part question. What will happen to velocity v if you point the fire extinguisher? So I know you're all saying, oh, it won't work because the spaceship's too heavy and the force from the fire extinguisher is too small. It will work. Very, very little. So whatever the effect is, it's a very small effect. But I want to know, what's the effect? What would the effect on V be if you point this fire extinguisher backward and fire it? What would happen to V? Then, what would happen to speed V if you put the fire extinguisher forward and then shoot foam forward? And finally, what happens if you take the fire extinguisher and shoot some foam sideways, perpendicular to V? What would happen to the speed or velocity v in all 3 cases? Okay, so pretty straightforward. If you shoot some fire extinguishing foam backward, the rocket ship will speed up. If you shoot it forward, it'll slow down. If you shoot it sideways, it would be a pretty small effect, depending on the mass and the velocity, but the rocket ship would turn slightly. It would turn a little bit. It would speed up a little bit, slow down a little bit, or turn a little bit. What's a way we can address all three things? Here's a hint. How can we describe all three things in one word? What will happen to a spaceship if you use a fire extinguisher out the window? What's that, Sage? You know the answer? Yeah. If the fire extinguisher shoots foam out with some force, the foam will exert the same force back on the spaceship. That's true. It's the third law. The force on the foam will equal the force from the foam, and that force will push the spaceship in the other direction. What happens when there's a force on a spaceship? Hazel? That force divided by the mass causes the acceleration. Yes, excellent. Good job. Everyone knows acceleration equals force over mass, as long as the net force, which it is in this case because we're in deep space. Okay, so an object moving that experiences some force will accelerate. It might accelerate forward or backward. It might speed up or slow down. We don't care about that. We care about when the force is sideways. When the force is sideways, it'll turn the object. It'll cause some sideways acceleration. If we have some object's velocity and some acceleration, and they're perpendicular, and they stay perpendicular, they're always perpendicular. Like, let's say this person aims their fire extinguisher sideways, and they hold it sideways the whole time. It's always sideways. The rocket ship's always going this way, and the fire extinguisher is always pointing this way. I guess we point the other way because it pushes the rocket backwards. But still, if these are perpendicular, well, the velocity starts like this, but acceleration, remember, is change in velocity over time. So the velocity will change and change and change and change and change. Until finally the velocity is like this. And the acceleration is like this. Still perpendicular. Well then, keep going. The velocity changed, acceleration. This will cause circular motion. Circular motion happens when acceleration is perpendicular to velocity. For reasons we'll come back to later, this acceleration is called centripetal acceleration. I'll tell you right now. It's called centripetal acceleration because centripetal means toward the center of the circle. So an object moving in a circle, it does accelerate. It doesn't speed up. It doesn't slow down, at least for now. But it's always changing direction, which changes velocity. That acceleration will be pointing toward the center of the circle that the object will move in. It's called centripetal acceleration. This is centripetal. You may have heard of the word centrifugal. Take that in your brain and just throw it away. It's garbage. We don't care about that. Centripetal acceleration. Think of a flower petal. Flower petals guide the bees toward the center of the flower. If you want a mnemonic to remember centrifugal, ask me in class. But centrifugal doesn't exist. It means away from the center, but it's not real. We care about centripetal acceleration. Alright, this is going to blow your minds. It's time for a big brain moment. So an object's going in a circle. Let's say this is the initial velocity. Okay, we know centripetal acceleration is delta v over t. Let's derive a formula for delta v over t. It's hard to give delta v as a number, but look at this v. The speed doesn't change. It starts like this, then it's like this, then it's like this, then it's like this. What would happen if we drew all the v's starting here? There's v naught. How will v look a second later? Like that. How will it look a second after that? How will it look a second after that? If we drew v at every point around the circle, we would get a full circle. The velocity starts out up and to the right, then it points right, then down right, down, down left, left, up, up right. It makes a full circle. Does that make sense? Around the circle, the velocity is always perpendicular to the surface of the circle. Another word is tangent, which is why this is called tangential velocity. Sometimes you write a t, vt. So at some point around the circle, the velocity is always in every direction of the circle. So what's delta v? It's not 0. It makes a full circle of radius v. Delta v is 2 pi v. Oh my gosh. Since it points in every single possible direction of a circle, over the full circle, the delta v is this circle. The velocity changes by going in a full circle, and the total circumference of that circle is 2 pi v. So this is the formula for centripetal acceleration, but we don't like this t. This is the period of time. How much time does it take the v vector to make that full circle? Well, it's the same amount of time it takes the object to make a full circle. Well, what's that time? We saw this formula before. Oh my gosh. If v equals 2 pi r over t, that means t is 2 pi r over v. That's the form for centripetal acceleration. An object moving in a circle is accelerating. It's not changing speed, changing direction, but it is changing velocity. And the rate of change of velocity with respect to time is that velocity squared divided by the radius. This is the form for centripetal acceleration. So an object that's going in a nice big circle slowly is changing its direction very slowly. It has a slow speed and it's a big circle, so this object has a very, very low AC, centripetal acceleration. But if I have an object going really fast, and then turns in a really small circle, like You ever hear like a sports car can turn on a dime? If something's going really fast and it goes and turns really small circle, it had a really high centripetal acceleration. What else do I feel like talking about today? That's centripetal acceleration. This is one derivation for centripetal acceleration. There's another one you can do that involves similar triangles, but basically, this is it. Centripetal acceleration is the tangential velocity squared divided by the radius of the circle. Just remember these two terms, centripetal acceleration, tangential velocity. The names kind of make sense. Toward the center, around the circle, tangent to the circle. Great lesson. Good job, Mr. Lamb.